with molecular structure is exciting. Okay, Chemistry 111. We're still in Chapter 10, and where we left off was looking at hybridization. And we were talking about the bonding of methane. And we said, well, methane has bonding. So if you look at the Lewis structure of methane, it looks like this. But that carbon is surrounded by 4 regions of electron density, the 1, 2, 3, 4 sigma bonds. And so it's going to adopt a tetrahedral molecular geometry because those 4 bonds want to get as far away from each other as possible. We said, well, that doesn't make sense based off of carbon's electron geometry, where we have a 2s orbital and a 2p, and there's 3 types of 2p orbitals. We have 2 electrons here and 1, 2 here. And we said, well, the way that we fix this is that we're going to take one of the electrons from the 2s orbital, put it in here. Then we have 4 unpaired electrons, which would give us our Lewis structure of carbon, so we can make 4 bonds. But there's a problem there too, because now you've got 4 orbitals, but 3 of them are p orbitals, and 1 of them is an s orbital. And so we said there's an answer to that too. And what we do is we make a set of 4 orbitals that are all degenerate, and that means they're all of equal energy. And we combined 1s and 3p orbitals, so we make what are called sp3 orbitals, and each one of them is going to have an unpaired electron, and that explains the tetrahedral molecular geometry of methane. And so hybridization is the mixing of 2 or more atomic orbitals to form a new set of hybrid orbitals. For example, S and P, or S and P and D. We're going to mix at least 2 non-equivalent orbitals. Hybrid orbitals have a very different shape from original atomic orbitals. I told you that I'm going to keep that different shape very simple. Okay, so when I drew the sp3 orbital, all I did was draw, something like that, and I wrote sp3 inside of it so that you would know it's sp3. Now you know that there's a smaller part of the lobe over here like this, but I left that out just to keep things simple. Second point is that the number of hybrid orbitals is equal to the number of pure atomic orbitals used in the hybridization process, right? You see that we have 1, 2, 3, 4 sp3 orbitals, but in order to make those 4 sp3 orbitals, I had to use 1s and 3p. So the sum of the number of atomic orbitals, 1s plus 3p, is a total of 4 atomic orbitals. They're used to make 4 hybrid orbitals. And then the third point, covalent bonds are formed by the overlap of hybrid and atomic orbitals, or hybrid orbitals with other hybrid orbitals. Well, the best way to understand hybrid orbitals is to look at them and to try some practice. But this just gets into more detail about that tetrahedral geometry, right, of our methane molecule. And again, I said, well, you have a carbon with a hydrogen, and all the bond angles are 109.5 degrees, like this. Everything's all perfect like that. And we said the only way that we can account for those 4 orbitals getting as far apart from each other as possible is that they're all the same. And so we form 4 sp3 hybrid orbitals. Again, the sp3 orbital is made from 1 s orbital and 1, 2, 3p orbitals. Therefore, it is 25% s and it's 75% p. This is an s orbital, and all of these over here are p orbitals. And that's why an sp3 orbital looks a little bit more like a dumbbell or a peanut than it does a sphere. Again, I told you that you can just draw the carbon and say, okay, well, it's got an sp3 orbital, sp3, we have another one coming out in front like this, sp3, we get another one over here, right? And as long as you write sp3 inside, the reader is going to know that what type of orbital it is. Okay, and here we go again. We see that carbon has 4 unpaired electrons, and we explained that each one of these is an sp3 orbital. All right, we explained this a couple slides ago. We said if we make 1, 2, 3, 4 hybrid orbitals, each one has an unpaired electron in it. So let's draw 1 unpaired electron here, 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 and here. We know that hydrogen has 1 unpaired electron. It doesn't need to hybridize because it's just a 1s orbital and it's got 1 electron in it. And then we can put that electron here. They're going to have opposite spin when they overlap like that to form a bond. And that is showing covalent bonding. So these regions where the s orbital of the hydrogen and the sp3 of the carbon overlap, that represents a bond, right? Because we know that in our methane molecule, whenever we see a line, whenever we see a dash here, that represents a bond, and each one of these bonds has 2 electrons in it. Here are the 2 electrons, right? Here are 2 electrons, here are 2 electrons, and here are 2 electrons. So this is just a way of representing the covalent bonds in methane and a way to explain molecular geometry. That's the whole point, or one of the major points of hybridization theory. If we look at ammonia, if you think of ammonia, the nitrogen atom in ammonia has 4 regions of electron density, doesn't it? It's got a lone pair, and it's got 1, 2, 3 bonds to hydrogen like this. But remember, each one of those groups, right, they're all spread out on the 4 corners of a tetrahedron, right? So again, this nitrogen has 4 regions of electron density. Its electron geometry is tetrahedral. How can we account for this? If we look at the electron configuration of nitrogen, and we're just going to look at the valence electrons, it's 2s2, 2p, 1, 2, 3. So we could write that out. We have a 2s, and then we have 1, 2, 3, 2p orbital. So we have 1, 2 in here, and then we have 1, 2, 3. Now, at first glance, it looks like everything's hunky-dory because we have 2 paired electrons. All right, we get a lone pair. Great, great. And then we have 3 unpaired electrons, and we've got 1, 2, 3 bonds. Great, great. No, there's a problem here because that doesn't explain why you would get 1, 2, 3, 4 orbitals that are all perfectly spread out like that. The only way it can do that is if they hybridize. And so, again, we're going to mix our 1s orbital and our 1, 2, 3p orbitals to make 4 degenerate. Degenerate is not somebody who belongs in prison or something like that, or somebody who's committed a crime. Degenerate in chemistry means equal energy. Okay, so now we've formed 4 degenerate sp3 orbitals, and look, we've got 1, 2, 3, 4, 5 electrons. This makes much more sense. We have our lone pair, and we have 1, 2, 3, 1, 2, 3 sigma bonds, or single bonds, if you will. All right, so again, each one of these nitrogen bonds has an electron in it, right? We have the 1, 2 electrons in the lone pair, and again, our hydrogen, each one of those hydrogens brings an electron to the table, right? Hydrogen is 1s1. And so again, and I'm repeating myself, but each one of these orbitals, these hybrid orbitals, is an sp3 orbital like that on our nitrogen. What about if I have a molecule like beryllium chloride, right? We looked at the Lewis structure of beryllium chloride earlier on. We said BeCl2, and we said that BeCl2, the beryllium, is surrounded by 2 regions of electron density, right? 2 bonds. Well, why would that be? Because beryllium only has 2 valence electrons. Let me prove it to you. If you look at the electron configuration of beryllium, it's helium, which accounts for the inner electrons, the 1s2 electrons, 2s2. Okay, but that doesn't make sense for the linear geometry. And if you're saying, well, why doesn't it make sense that it would form 2 bonds? Because, Mr. Dion, you told me that the Lewis structure of beryllium was simply beryllium with 2 unpaired electrons. But the problem is that if we look at this electron configuration, they're both in a sphere. That doesn't make any sense. That would mean they're paired up in a 2s orbital. That doesn't explain why they would get far apart from each other and form a linear geometry like we see in beryllium chloride. Well, the answer is this, okay? Because beryllium's 2 valence electrons are in a 2s orbital. What else do we have in the second period? Besides 2s, we have 1, 2, 3, 2p orbitals. So what we're going to do is we're going to take one of those electrons and we're going to put it in a 2p orbital. So now we're going to take the 1s orbital and the 1p orbital like that, and we're going to hybridize them, right? We're going to make a sp orbital, and each one of them is going to have an unpaired electron in it like that. If I've got 2 orbitals that are identical, they're going to want to get as far away from each other as possible. And so what I'm going to end up with is my beryllium is going to have an orbital over here like this, and it's going to have another orbital over here like this. This is an sp orbital, and this is an sp orbital. Each one has an unpaired electron in it like that. Okay, and that explains why beryllium chloride has a linear geometry. Before we move on, let me just address the chlorine, because if we think about the Lewis structure of chlorine, chlorine is a halogen, It has one unpaired electron. Chlorine doesn't have to hybridize, right? Because it doesn't have a molecular geometry, right? If it's a terminal element, it doesn't have any molecular geometry associated with it, right? The beryllium does because it's got two elements attached to it. The chlorine doesn't. Okay. All right. So what about that chlorine? Well, if we think about those valence electrons, okay, if I look at the electron configuration of chlorine, it's this. It's so let's do it like this. Chlorine is neon, and then we have 2s2, and then we have 2p5, like that. That means that in the p orbitals, and I have 1, 2, 3 p orbitals. So my 2 p orbitals, I've got 1, 2, 3, 4, 5. I've got an unpaired electron here, and I have no molecular geometry to justify. And so my chlorine, actually what it really looks like in reality is that it's a chlorine like this, and it's going to have one p orbital in going vertically like this. It's going to have another one going horizontally like this. Each one of these will have 2 electrons. You know, maybe I should just keep it simple. I'll put the one in the back and the one coming up in front like this, okay? That will have 2 electrons in it, and then one of them is going to have 1 electron. And if you're wondering, like, why did they just draw it like this? Where are the other 2 p orbitals? They left them out on purpose, okay, just to make it simpler and easier to look at. So they basically just deleted all of this spinach here, you know, and they just tried to show, you know, that the chlorine has 1 unpaired electron and thus it can bond to the beryllium. Okay, so that's hybridization in beryllium. So that's a new type of orbital. That's it. So now we've looked at sp3 orbitals and sp orbitals. You've probably noticed something, and I'll just kind of mention this. There's not a lot of room here, but you'll probably notice something along the way about the way I'm writing things, and that's it. When I talked about an sp3 orbital, I drew it like this, and I wrote sp3. When I talked about an sp orbital, I drew it like this, and I wrote sp. I'll tell you what, in the next slide, we're going to look at an sp2 orbital, and I'm going to draw it the exact same darned way. Okay? So all of these orbitals, they do have slightly different shapes, of course, because they're comprised of different percentages of s and p orbitals. But when I draw them, or when the book shows them, they're always going to look like this. Okay, they're always going to look virtually identical. Okay, so what about sp3? Let's say I have something like boron trichloride, BCl3. Well, if I look at the valence electrons in boron, we have the core electrons of helium, then we have 2s2, 2p1. If we take a look at that, we've got a 2s, it's got 2 electrons, we've got 3 2p orbitals, there's only 1 electron. That does not explain why boron trichloride forms a trigonal planar molecular geometry, does it? Because the way this is shown, I mean, I've got 2 electrons in an S in a sphere, and I've got 1 unpaired electron in a 2p orbital. What I'm going to do is I'm going to hybridize some orbitals, right? But since I only have 3 regions of electron density, I only need to hybridize 1, 2, 3 orbitals. What's that going to look like? Let me show you. It's going to look like this. We're going to have an s orbital and 1 2p orbital. So now we've got s, and we only took 2p orbitals, so it's sp2. We've got a total of 1, 2, 3 electrons. There you go. That's why my boron, right? My boron is going to be surrounded by 1 sp2 orbital, 2 sp2 orbitals, and 3 sp2 orbitals. And they're going to seek to get as far away from each other as possible. They each have 1 unpaired electron. Look, 1, 2, 3, like that. Here they're showing boron trifluoride in this picture here, but fluoride is a halogen, as is chlorine, and so the same thing applies. That our chlorine, for example, in my boron trichloride, it's going to have, you know, a p orbital. It's going to overlap like this, my chlorine, and then I'm going to have an unpaired electron in there, so I form a bond. This chlorine, this is a p orbital again, and then this chlorine here. Okay, and I could have chosen boron trifluoride. I just got ahead of myself here. So here's my chlorine. Here's my chlorine. Anyhow, you get the idea. Okay, so we've got sp orbitals, sp2 orbitals, sp3. If you're wondering, you know, how do I predict this, right? Information, Mr. Dion, and I've only covered a little bit of it, right? I've covered sp, sp2, and sp3. We still have sp3d and sp3d2 orbitals or hybrid orbitals to look at, but here's the quick and dirty answer, okay? The first thing you're going to do is you're going to draw a Lewis structure. By now, you should know how to draw a Lewis structure. Then you're going to count the numbers of lone pairs and the number of atoms bonded to the central atom. Okay, so you count lone pairs and atoms. I can't stress that enough. Let's highlight that. Lone pairs and atoms. Those are the two things. Okay, if the total of lone pairs and bonded atoms equals 2, the hybridization is SP. Okay, if the total of lone pairs and bonded atoms is 3, sp2. If the total of lone pairs and bonded atoms is 4, you've got sp3. If it's 5, you've got sp3d. And if it's 6, you've got sp3d2. Now, if you're waiting for a rationale as to where sp3d and sp3d2 come from, we're going to look at some examples that will cover that. All right. Well, here's a great, kind of quick table that you can use to help you determine hybridization. So this is table 10.4 or 10.4 in your textbook. Okay. If you've got, again, the total of lone pairs, so this is here, would kind of be the total of lone pairs and atoms. If it's 2, it's sp hybridized. If it's 3, it's sp2. If it's 4, it's sp3. If it's 5, it's sp3d. And if it's 6, it's sp3d2. Okay? Again, that table is going to be a valuable resource moving forward when you're practicing problems that involve hybridization. Well, let's look at some examples here. It says determine the hybridization state of the central or underlined atom. Well, there's no atoms that are in there. Anyhow, the central atom in each one of these. Okay, so we're going to look at the hybridization of all of these. I'm going to do the first two kind of quickly because we looked at examples that were very similar to these ones here. What the heck am I talking about? We looked at an example that was close to this one too. Anyhow, let's take a look at all of them. I'm going to jot them down here. So beryllium hydride, aluminum iodide, and phosphorus trifluoride. Okay, well, let's, again, we're going to describe the hybridization state of each one of these central atoms. Now look, what's the strategy going to be here? Okay, your strategy is simply going to be to draw a Lewis structure, right? That's the first one. By now you should know how to draw a Lewis structure. Then you're going to use VSEPR, valence shell electron pair repulsion theory, to determine the electron pair arrangement surrounding the atom. So that means you're going to look at the number of atoms that surround the central atom and lone pairs. Okay, then you can use table 2 or 10.4 to determine the hybridization of the central atom. So 1, 2, 3 step process. Well, let's solve it here on a blank piece of paper. I think that's probably a better way to do it. And we'll start with beryllium hydride, BeH2. All right, and we've already covered beryllium, so I'm going to go over it kind of quickly. But by now you should know that the Lewis structure of beryllium hydride would look something like this. It's only going to have 2 covalent bonds. Why? Why would there only be 2 covalent bonds to the beryllium? Because if I look at the electron configuration of beryllium, it's helium 2s2. If I have 2 electrons that are paired up in a 2s orbital, 1, 2, that doesn't account for there being 2 bonds. Those electrons are paired up in an s orbital. That's impossible. Why would I have an electron over here and an electron over here? The reason why is because of hybridization, right? We know that we have the 2p orbitals available because they're also in the second period. And so what we're going to do is we're going to take a 2s orbital, right? That's got the electron. So we're going to take the 3 2p orbitals and we're going to take one of those electrons and we're going to move it in here. Let's take a look at what that would look like. When we do that, we're going to have 1, 2 hybrid orbitals, which is going to be made from 1 s orbital and only one of the p's. So that's why we call it an sp. There's going to be 1, 2 electrons in it. Then we have 2p orbitals left over. 2p, and there's nothing in those. Just forget them. Okay? All you're concerned about are the hybrid orbitals that have electrons in them. So now we've got our beryllium that's sp hybridized, right? It's going to have an sp orbital here and an sp orbital here. Because of VSEPR, valence shell electron pair repulsion, they're going to get as far away from each other as possible. They've each got an unpaired electron like that. And then we have the hydrogens. Hydrogen is just a 1s, and it's got 1 electron. Another hydrogen here. We'll just label those hydrogens 1s, okay? And there we go. That explains the molecular geometry and the hybridization of the central atom of beryllium hydride. It is sp hybridized. Let's take a look at aluminum iodide. This is ALI3. We draw a Lewis structure of ALI3. It looks something like this. The aluminum is surrounded by 3 atoms and no lone pairs. Right away, if you went to table 10.4 directly, you just say, hey, the central atom, if it's got 3 atoms surrounding it, okay, and 0 lone pairs, just by looking at table 10.4, you'd say this is sp2 hybridized. Okay, if we want to look at it a little bit deeper, we can look at the electron configuration of aluminum, which is neon 3s2 3p1. Right, that's 3s with 1 2 and 1 2 3p orbitals, and we've got 1 electron here. That doesn't account for there being 3 bonds, does it? Why would 3 electrons get as far away from each other as possible if 2 of them are paired up? The answer is what? Hybridization. So we're going to hybridize some more, aren't we? We're going to need 3 orbitals that are hybrid orbitals. So we're going to mix 1s and 2p to form sp2, and then we're going to have 1 2 3 unpaired electrons, right? We took this electron and we put it in here. And now we've still got an unhybridized 3p orbital left over, right? We didn't use this one. We're just going to put it there. Don't even worry about it. Don't stress, okay? You can sleep tonight. Don't worry about it. Okay, so that would explain why our aluminum is surrounded by 1 sp2 orbital, another sp2 orbital, and another sp2 orbital like that. Why do they all adopt this, 120-degree bond angle? Because they're trying to get away from each other, right? Quit crowding me. We've got 1 2 3 unpaired electrons, and then my iodide. I'll just go over this quickly. Those are all p orbitals, right? They've each got an unpaired electron like that, and like this. Okay, forgive me for my artistry, but anyhow, of course, these are all from iodine, so these are actually 5p orbitals, 5p. Anyhow, you get the idea. All right, and then we're going to look at what? Phosphorus trifluoride. Okay, so PF3. Let's go over this one really quick. You know what? Let's just pretend we were only going to use table 10.4. Okay, if we look at PF3, you would draw a Lewis structure. You'd say, okay, 5 valence electrons here. Fluorine is a halogen. It's got 7 valence electrons. There's 3 of those. There's 21 plus 5. That equals 26 valence electrons. Phosphorus is going to be my central atom. I know that fluorine is a rule. It always only has 1 bond and 3 lone pairs. There's no exceptions to that. I've used up 24 electrons. I've got 2 left over. There you go. So this phosphorus atom, my central atom, is surrounded by 1 2 3 bonds and 1 lone pair. The hybridization is going to be sp3. Nothing more than that. That would be simply using table 10.4. That would be the strategy that I applied solving that problem. If we back up here, sorry, I'm going to have to do a lot of rifling around here. Fine. So here's what it says in the solution. It says the ground state electron configuration for phosphorus is 3s2 3p3. Right? If we write that out, we have 3s 1 2 3p. There's 1 2 3. Okay. There are 4 pairs of electrons around the phosphorus. Therefore, the electron pair arrangement is tetrahedral. Right? That's electron geometry. The molecular geometry is trigonopyramidal. We conclude that phosphorus uses sp3 hybrid orbitals in bonding to fluorine because sp3 orbitals have a tetrahedral arrangement. Again, this is using table 10.4. Now, I'm not going to provide that table to you. You have to familiarize yourself to look, at the solutions here, which explain how we form hybrid orbitals. Now, there's something that I don't like about this representation of hybrid orbitals. I always put the lone pair at the beginning, so 1 2, like that. That's how I would write it. They put them here at the end. I don't dig that. I don't think that's cool. But anyhow, it does show the correct answer regardless. And then it says here, we predict the geometry of the molecule to be trigonopyramidal, and the fluorine phosphorus fluorine bond angle is going to be a little less than 109.5. Why? Right? The phosphorus is surrounded by a lone pair. 1 2 3 fluorines. I should fill in all my lone pairs on my fluorines. And we know that the lone pair is going to repel, it's going to push these bonds down a little bit, which is going to cause the bond angle here to be a little less than 109.5 degrees. Now, you don't have to have bond angles memorized outside of things like the 109.5 degrees. As long as you say, hey, Mr. Dion, it's less than 109.5, that's good enough for me. Okay, that'll be good enough to answer any question on your exams. Okay, let's try one more. It says, describe the hybridization state of the phosphorus and phosphorus pentabromide. You can see that the phosphorus is surrounded by 5 atoms and 0 lone pairs. If I go to table 10.4, look, where are we? We back up. Where was table 10.4? There we go. There's table 10.4. All right, you can see that when central atom is surrounded by 5 atoms or 5 groups, 5 regions of electron density, it is sp3d, hybridized. Let me show you how that works. Because now we're getting into d orbitals. Well, remember that phosphorus is in the 3rd period, right? So we have 3s, 3p, and we also have 3 d orbitals at our disposal. If we look at the electron configuration of phosphorus, it's neon, 3s2, 3p, 3. That looks like this. I have a 3s with 1, 2 electrons, 1, 2, 3, 3 p orbitals, 1, 2, 3 in each of them. That doesn't account for the phosphorus having 5 bonds, does it? Because in order to form a bond, that means the phosphorus has to have 5 unpaired electrons. Well, if I take these orbitals and I move them down here, I know that I also have at my disposal 1, 2, 3, 4, 5, 3 d orbitals. What if I took this electron here and I moved it into a 3d orbital? Then what would I have to mix? I'd have to mix 1s, 3p, and 1d orbital. What would I end up with? I'd end up with 1, 2, 3, 4, 5 hybrid orbitals, and I would have 1s, 3p, and then 1d. And then I'd have 1, 2, 3, 4, 5 unpaired electrons. I've still got this left over, right? 1, 2, 3, 4, 3d orbitals that I didn't do diddly squat with. You know what? Don't worry about them. Okay? Don't worry about those at all. But that explains the hybridization of that phosphorus and phosphorus pentabromide, 5 bonds. Okay? This is just another representation of it like this. And again, because we have 5 regions of electron density around the phosphorus, it's going to be trigonal bipyramidal. All right, give me a thumbs up if you follow me on hybridization. Even if you're with me 50% of the way. Hybridization is one of those things that it'll take you some time to study it, and look over it and ruminate on it before you understand it. I don't expect any students to say after one lecture, hey, I understand everything there ever was to know about hybridization. It definitely takes practice. Definitely takes practice. Okay, well, let me just look ahead in my notes here for a seckie. There we go. And I want to talk to you guys about something. I'm just going to go back to my blank document. We'll just wrap here a little bit about chemistry for a few minutes before we get back into the slides. I want to talk to you about some molecules that have carbon in them. For example, we've already looked at methane, CH4, one of the major components of natural gas. We said that the hybridization of the carbon was sp3. Well, what if I have a carbon in this molecule? Okay, if I have a carbon that has a double bond to it, and you can see that there's a plane of symmetry running down this molecule, so both of these carbons are identical. My question is, what's the hybridization of this carbon? Or what if I had a molecule where I had a triple bond, between the 2 carbons? What's the hybridization of the carbons there, right? Because we can see, again, there's a plane of symmetry. So what would the hybridization be of those carbons there? The first thing I want to tell you is this. Whenever I have a single bond, so the word I'm saying is single, S-I-N-G-L-E, single bond between two elements, that's called a sigma bond. Okay, so this is called a sigma. So you guys know the Greek alphabet? I'm sure you have it all memorized, right? So this is the symbol for sigma. And then, of course, you know the symbol for pi. Everybody knows that. Okay, so anytime I have a single bond, that's called a sigma bond. So here, that's a sigma bond. This is sigma, that's sigma, that's sigma. A single bond is a sigma. Here's a sigma bond. This is a sigma bond. Okay, walla walla, right? Let's identify, like this is a sigma bond, like that. Okay, anything that's just a single line between two elements is a sigma bond. When I have a double or a triple bond, okay, the first bond, and it doesn't matter if you point to the top one or the bottom one, that's neither here nor there. But the first bond is always a sigma, okay? Gotta clean that sigma up, okay? Same thing over here in the triple bond. The first one is always a sigma, and I could, and again, it doesn't matter. I could have labeled the top one. Just one of them is a sigma bond, okay? Anything after a sigma bond, so if you have a double or triple bond, the other bonds are going to be pi bonds. Like this is called a pi bond. This is called a pi bond. This is called a pi bond. Pi bonds are weaker than sigma bonds. Okay, so hear ye, pi bonds are weaker. They're not as strong as a sigma bond. And we're going to look at how pi bonds are formed in this chapter, but we're not there yet because I want to talk about the hybridization. But I want you to understand what a pi bond is. Okay, so a couple things about pi bonds. Okay, so we'll say here pi bonds are weaker. Okay, weaker bonds. We'll put here weaker and sigma, and okay, are formed from side by side overlap of p orbitals. Right? You guys know what a p orbital looks like, right? A p orbital looks like this. Okay? So if I have two p orbitals, if I have a p orbital here, and if I have another p orbital here, and they overlap like this, okay? This is what we call head to head overlap. Okay, if they each had an unpaired electron, that would be head-to-head overlap, and that would be forming a sigma bond, okay, which is really strong. If I have two p orbitals and they overlap side to side, so here's a p orbital with an unpaired electron, okay, and if I have another p orbital, I'm going to try my best here, and it overlaps like this, side to side like that, that's when you form a pi bond. Now, it's not intuitive, okay? It looks like the side to side. You're like, come on, man, it overlaps here and it overlaps there. Shouldn't it be stronger? No, it's not. Okay, it's not as efficient. And again, it's not intuitive just by looking at the pictures, but side to side overlap is weaker, okay? And that's how pi bonds are formed. Okay, so we got head-to-head overlap of orbitals. That forms sigma bonds. And side-by-side overlap of pi bonds, which are unhybridized. So side pi bonds, and we'll put here unhybridized, okay? That forms a pi bond. And we'll put here sigma bond. Why don't we put here hybrid orbitals. Hybrid orbitals like that. Okay? So those are, some big differences, and this is kind of Mr. Dion's way of explaining it to you, but I find it's a lot easier to follow things this way. Okay, so with all that information in mind, let's get back to this molecule again. Get back to this molecule here, where we have a double bond between the two carbons here. And let's talk about the hybridization of each one of those carbons. I'm just going to clean up this sigma bond, now that you know what a sigma bond is, right? Again. There we go. So let's talk about the hybridization. Again, both of these carbon atoms are identical, but this carbon has 3 sigma bonds, doesn't it? And it's got 1 pi bond. Well, again, the sigma bonds are going to come from hybrid orbitals, and the pi bonds come from unhybridized orbitals. Well, if there's only 3 orbitals that are hybridized, 1, 2, 3, that would mean that carbon must be sp2 hybridized, wouldn't it? And that's correct. Okay, let me show you what that plays out like when we look at the electron configuration. My carbon has an electron configuration of helium, which is the core electrons, 2s2, 2p2. Okay, if I look at the orbitals 2s, I've got 2 electrons paired up in here, and then 1, 2, 3. And we've already looked at this tonight. This isn't new. Okay, I've got 2 unpaired electrons and 2 electrons paired up. That doesn't explain why I would form 3 bonds, does it? Because I'm going to need to have 3 unpaired electrons. I'm also going to need an unpaired electron to form my pi bond. But the thing is, the pi bond is going to be in an unhybridized orbital. What does that mean, Mr. Dale? Well, let me show you. What we're going to do is we're going to mix 3 of those orbitals. 1, 2, 3. We're going to mix 1s and 2p orbitals together. So we're going to have sp2, and we're going to have 1, 2, 3 unpaired electrons in those. That explains the sigma bonds, right? Okay, I have 1, 2, 3 sigma bonds. What have I got left over? I'm going to have 1, 2p orbital. I'm going to write it over here, and that is going to have an unpaired electron in it. That's an unhybridized orbital, right? That's just a plain old 2p. It's got nothing to do with sp2s and ds and whatever. Okay, it's not a hybrid orbital. That's unhybridized. So that represents the pi bond. Okay, so that means the hybridization of the carbon in this molecule, both of the carbons here, okay, both carbons are sp2 hybridized. What about the molecule that had the triple bond? Let's take a look at that. Right? Each one of these carbons has 1, 2 sigmas, so 2 sigma bonds, 2 sigma bonds, right? And each one of these carbons has 1, 2, 2 pi bonds. That means it's going to have 2 unpaired electrons in hybrid orbitals and 2 unpaired electrons in unhybridized orbitals. Let's start over. We know that our carbon is helium, 2s2, 2p2. We have our 2s with 1, 2 electrons. We have 3 degenerate 2p orbitals. Again, that doesn't explain why I would form 4 bonds, because I've got 2 electrons that are paired up. But now I only need 2 electrons in hybrid orbitals. And so I'm going to put 2 of them together, and I make an sp orbital. And then I'm going to have 2 2p's left over. 1, 2 electrons in my sp, my hybrid orbitals, which represent my sigma bonds. And then I'm going to have 2 electrons left over in 2p orbitals, which are unhybridized, which represent my pi bonds, like that. Okay, there we go. Give me a thumbs up if that helps a little bit in understanding, where this comes from. Because if I really wanted to, give you the quick way of explaining this, all I would have said is, well, if you look at the carbon in the molecule with the double bond, that molecule is called ethylene. It's surrounded by 2 atoms and no lone pairs, right? Both of these, think about it. Both of these carbons have 3 atoms and no lone pairs. Therefore, based off of table 10.4, done. sp2, right? Problem solved. If I look at the 2 carbon atoms in this molecule, this is called acetylene. It's the same acetylene that's used in acetylene torches for welding. Think about it. This carbon is surrounded by, the carbon on the left, for example, it's surrounded by 1, 2 atoms, no lone pairs. Hey, sp2, done. Right, but this shows us the rationale. Okay, and this is important. You do have to know this. Okay, so again, to recap, both of these carbons are sp2 hybridized, and both of these carbons are sp hybridized. So now I've looked at these. Let's see here. Let me back up. This is a view of bonding in ethylene and acetylene. Well, I think I can show you a lot clearer than it's shown in these pictures here. So let me just go back here. But before I do, I just want to point out that when we have a single bond, right, like in methane, right, if we have single bonds like in methane, those are all single bonds. Those are all sigmas. If you have a double bond, okay, and this goes for any double bond, right? It's comprised of what? One sigma, right? One of them's a sigma. The other one's going to be a pi. And if you have a triple bond, just don't lose sight of this because we're going to be talking about sigmas and pi's a lot, right? You're going to have one sigma bond. Again, doesn't matter if it was the top or the bottom. And then you're going to have two pi bonds. The two pi bonds, 1, 2. Okay? So I want you to keep that in mind. And now I'm going to show you where they came up with these sketches, like this here. You see all this funny sketch here, and then this sketch here. This one kind of looks like a hot dog, doesn't it? And again, I'm going to show you where these sketches come from. Okay? So let me show you quickly. Let's go back here. And we'll go back to our ethylene molecule, right? C2H4. Okay, so ethylene, which is C2H4. We already drew the orbital, the fluid structure, and we determined that the hybridization of those carbons, and now I'm just going to skip right ahead to the hybridization, was sp2, right? 1, 2, 3, and then they had a 2p with one unpaired electron, like that. Okay. We also know that hydrogen, and by now you know this off by heart, is just 1s1, so it's just going to have one electron. Okay, well, let's think about those carbons. Let me draw a carbon. Okay, and maybe I'll draw it a little smaller. Okay, the carbon is going to be surrounded by 1, 2, 3 sp2 hybrid orbitals. How are they going to get as far away from each other as possible? They're going to adopt a trigonal planar molecular geometry. Look, I'm going to have one sp2 orbital like this. It's got an unpaired electron. I'm going to have another one. Look, I'm just thinking trigonal planar here. sp2. It's going to have an unpaired electron. And I'm going to have another one going down here. sp2. Again, I'm trying to keep that bond angle around 120 degrees. Okay. Well, again, this is supposed to be trigonal planar. I'm trying my best here. Well, there's also going to be a pi bond. We're going to have an unhybridized 2p orbital. Well, what does a p orbital look like, right? A p orbital looks like a p-net. Okay, well, if all of these sp2 orbitals are, let's say they're all on the plane of the board, like this is flat as a pancake, that would mean that the p orbital would try to get away from those. So one of the lobes would go in the back, like this, okay? Again, I'm drawing my 2p orbital, and another one would kind of come out in the front, like this. And again, I'm trying my hardest to draw it, okay? Well, I have a second carbon atom that's going to look exactly like this, won't it? What's that going to do? Well, I'm going to have my other carbon atom. So I finished drawing this one. Now I'm on to this one. It's going to have an sp2 orbital that's going to overlap, okay? Right over here, sp2. What happens when I overlap hybrid orbitals? I make a sigma bond, right? This is a sigma bond right here, okay? I'm going to have another sp2 orbital here and another sp2 orbital here. Label them. We each have an unpaired electron like that. And then I don't want to forget my 2p orbital. Our lobe's just going to be going in the back like this. I'll label it, no, 2p, put an unpaired electron, and the other one's going to be coming, out in front like this, like that. So there's my 2p. Okay, so let me show you what else is going on. First, let's finish the sigma bonds. I've got 4 hydrogens. Each one of those hydrogens is just a 1s, right? This is just a 1s with 1 electron. That's a sigma bond. I've got another hydrogen. That's a 1s. I forgot to put in my electron here in red. Okay, that's another sigma bond. I've got another hydrogen over here overlapping, right? That's another sigma bond. And I've got another hydrogen over here. And that's a sigma bond. Look at how many sigma bonds. 1, 2, 3, 4, 5. Well, look at 1, 2, 3, 4, 5. We have one more bond, and that is the pi bond. How do I represent that? Well, remember, I told you that a pi bond, right? A pi bond was a result of the side-to-side overlap of 2p orbitals. Now, I told you that they touch, right? They overlap like this. Doesn't look like these are touching, does it? They're way too damn far apart. Why are they too far apart? Because I'm limited by my drawing skills, okay? I just leaned over the desk, okay? I'm limited by my artistic abilities, okay? I'm not that great of an artist. So here's what I do. Since my 2p orbitals are so damn far away from each other, I got one over here, and then I have one, you know, a million miles apart when they're supposed to be overlapping. Here's Mr. Dion's workaround. Are you ready? To draw a line to show that they're touching. Okay, literally, and you're like, you're kidding. No, I'm not kidding. That's what I do. So I draw a line here and a line here like that. And that is my pi bond. Okay, now hold on. Don't fall into a trap. Because you're like, hey, Mr. Dion, you got a line here and a line here. That's 2 pi bonds, baby. No, 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 no. That's 1 pi bond. Okay, 1 pi bond formed by the overlap of 2 p orbitals. Okay, now in this case, they happen to be 2p orbitals, but it could be 2 3p orbitals or 2 4p orbitals. Okay, give me a thumbs up if you follow me on this. This is called an orbital overlap diagram of ethylene. It shows all the hybrid orbitals, the unhybridized orbitals of hydrogen, and explains the hybridization of the carbons and explains the molecular geometry. All right, well, let's look at the acetylene. I'll do this one a little bit quicker. So acetylene is C2H2. It looks like this. We've got a triple bond between our 2 carbons. Okay, we already know that the hybridization here is sp. Why would that be? Because we know the carbon, and I'm going to skip right ahead to the hybrid orbitals. We've got sp, we've got 1 unpaired electron in each of those, and then we've got 2 2p orbitals and 1 unpaired electron in each of those. What's a carbon going to look like? It's going to have an sp orbital going over here with an unpaired electron, and it's going to have an sp orbital trying to get as far away from as possible from the other one with an sp. With an unpaired electron in it. You've got the other carbon over here. That's going to overlap, right? This is an sp. There you go. There's your first sigma bond. Now I've covered this one right here. Okay, then you're going to have another sp hybridized orbital over here with an unpaired electron. What else? Let's get to the hydrogens. That's easy, right? We know we have a 1s here with an unpaired electron. We get another 1s over here with an unpaired electron. Now I've got all my sigma bonds accounted for. How do you account for 2 pi bonds, Mr. Dion? Right, I can see how all of this is linear, right? I can see how if this is a hydrogen and this is a, right? I can see how this this is a linear arrangement here, and then this is linear here. Okay, great. So this is how I'm going to draw them. I'll draw the p orbitals. I'll draw one in blue. So one of them is going to be perpendicular to those. So I'm going to have a 2p. An unpaired electron and a 2p, right? With an unpaired electron, that's the first one. Okay. Remember, there's 2 carbons, right? This is just 1 carbon, but there's 1, 2 of them. Okay. So that's those. I'm going to draw the orbital overlap. Okay. Again, this is Mr. Dion's patented method. Okay. For the second 2p orbital, again, they're going to try to get as far away as possible. So they're going to be perpendicular to the other 2p orbitals. So you're going to have a 2p orbital going in back, and you're going to have another one kind of coming out in front like this. You're going to have an unpaired electron. You're going to have another one going in the back like this. This one coming out in front, 2p, an unpaired electron. Make sure you show them with opposite spin, and they're going to be touching. This is, wow, look at that 3D. It's like it's headed straight for us, okay? There you go. That's Mr. Dion's orbital overlap diagram. Bada boom, bada bing. And what I just drew was my representation of what's shown right here, okay? This is kind of their way of doing it. If you look at an electrostatic potential map of acetylene, okay? All right, this is the molecule that they're showing here. The red means the electron density, right? The delta negative, and this is the delta plus over here. So you see that most of the electron density is actually localized in between the 2 carbon atoms, which is interesting in the point of view of reactivity. Now we have a problem here, and I've spent a lot of time talking about hybridization this evening. So I'm going to kind of do a quick version of the solution to this problem, relying a little more heavily on table 10.4, but it says here, describe the bonding in the formaldehyde molecule, whose Lewis structure is shown right here. Assume that the oxygen atom is sp2 hybridized. I don't even know why they had to give us that help, right? Why did they have to tell us that oxygen is sp2 hybridized? Look, the oxygen is surrounded by 1, 2 lone pairs and 1 sigma bond, right? It must be sp2 hybridized, right? Because this is a pi bond. You know what? To heck with it. Let's do it the good way. Let's do the whole thing. Okay, if we think about formaldehyde, which is this molecule right here, okay, well, we've already covered the carbon. All right, the carbon has 3 sigma bonds and 1 pi, so that means the carbon is going to be sp2 hybridized, 1, 2, 3, and it's going to have an unhybridized 2p orbital. Let me show you how the oxygen works, since we haven't looked at oxygen yet. If I think about the electron configuration of oxygen, it's helium. We're going right down here to the ground state, 2s2, 2p4. That would look like this, 2s, 1, 2, 3, 2p. So I've got 1, 2 in here, 1, 2, 3, 4. Now you might look at that and say, hey, perfect, perfect. 2 lone pairs, 2 pairs, 2 bonds, 2 unpaired electrons. No, right? Because that doesn't account for the fact that the 2 lone pairs and the sigma bond tried to get as far away from each other as possible, right? So now we've got to make hybrid orbitals. So what we're going to do is we need to do the mixing of 3 orbitals and have 1 unhybridized orbital to form my pi bond, right? Because one of these bonds is a pi bond, isn't it? Now I'm going to have, look, I've got a total of 1, 2, 3, 4, 5, 6. If I have 1 electron in a 2p orbital, that means I've got 1, 2, 3, 4, 5. Now it makes more sense, right? My carbon looked like this. Get an sp2, get an sp2, and let's get another sp2. They're all trying to get as far away from each other as possible. We've each got an unpaired electron. Look, let's do the hydrogen quickly. A 1s and a 1s, okay? Now, how do we draw the oxygen? Now, I'm kind of running out of space here, so let me just do some moving of things. Come on. Just give me 1 second here. iPad's a little slow at times. Okay, so my oxygen, why don't I draw it? No, I'm going to draw it in black. My oxygen is also sp2 hybridized. Look, maybe I'll move it down a little more. Okay, it's going to have an sp2 orbital, right, with 1 unpaired electron. That's going to form my sigma bond, right? And it's got 2 sp2 orbitals. They're going to get as far away from that one. One over here, this is sp2, but it's got 2 electrons paired up. That's a lone pair. This is my other lone pair. But look, they both have an unhybridized 2p orbital, don't they? Right? I forgot to put my electron over here. I messed that up. But anyhow, so the oxygen is going to have a 2p. Right, this is a 2p with an unpaired electron, and the carbon also has a 2p with an unpaired electron. They're going to overlap like that. This represents my pi bond. Here's one of my sigmas. This is a lone pair here. This is a lone pair here. This is a sigma bond, and this is a sigma bond. And that is the orbital overlap diagram of formaldehyde, showing the hybridization of the oxygen and the carbon. That's the whole thing, from soup to nuts. Take it to the bank, people. Okay. If that doesn't light your fire, your wood's wet, right? You know, it's exciting stuff. You know, hybridization is really, really fascinating, I find. Okay, well, give me a thumbs up if you're like, hey, I think I understand hybridization better than I did when I read the chapter 6 times, like you were supposed to. You're always supposed to read the chapter before coming to class, right? Of course, you're like, of course, Mr. Dean, I've been doing it all semester. Right? I always read the chapter, you know, get something to eat, you know, sit down and just enjoy the book, you know, while I'm munching on something. Anyhow, okay, I digress. Where was I? Now we're all the way to something new. So now we're going to switch from hybrid orbital theory to MO theory, or molecular orbital theory. What we just looked at, the valence bond theory, is one of the 2 quantum mechanical approaches that explain bonding in molecules. It accounts, at least qualitatively, for the stability of the covalent bond in terms of overlapping atomic orbitals, like we just saw. Using the concept of hybridization that we just looked at, valence bond theory can explain molecular geometries predicted by VSEPR, right? That's what we just went over. However, the assumption that electrons in a molecule occupy atomic orbitals of the individual atoms is really only an approximation, because each bonding electron in a molecule must be in an orbital that is characteristic of the molecule as a whole. In some cases, valence bond theory cannot satisfactorily account for observed properties of molecules. Take, for example, oxygen, O2. If we look at the Lewis structure of oxygen, which is shown right here, and if we look at its hybridization, it shows all of the electrons as being paired up, right? Both of these oxygens are sp2 hybridized, and we can show how, if we drew an orbital overlap diagram, everything would be paired up. But according to, this description, all of the electrons in oxygen are paired, and therefore oxygen should be diamagnetic. That would mean it is not attracted to a magnet. It's actually slightly repelled, right? That's the definition of diamagnetism. However, this is a magnet shown right here, and there's actually liquid oxygen being held between the poles of a magnet. So that means that oxygen is actually paramagnetic. This finding suggests a fundamental deficiency in valence bond theory, one that justifies searching for an alternative bonding approach that accounts for the properties of oxygen and other molecules that do not match the predictions of valence bond theory. Magnetic properties, like shown by this oxygen molecule here, of molecules are sometimes better explained by another quantum mechanical approach called MO theory, or molecular orbital theory. Molecular orbital theory describes covalent bonds in terms of molecular orbitals instead of atomic orbitals. And these molecular orbitals result from the interaction of the atomic orbitals of the bonding atoms and are associated with the entire molecule. So it's a bigger picture. The difference between a molecular orbital and an atomic orbital is that an atomic orbital is only associated with one atom. And so, again, molecular orbital theory, which is what we're going to concentrate on now, or MO theory, bonds are going to be formed from the interaction of atomic orbitals that are going to form bigger orbitals called molecular orbitals, which deal with the entire molecule. Okay, so since they deal with the entire molecule, you can imagine when we're dealing with big molecules that MO theory gets really complex. And so in this class, we're just going to kind of, touch the tip of the iceberg, and we're going to look at simple examples of MO theory. Now, of course, they're not simple when you're learning it, right? But we're going to just kind of scratch the tip of the iceberg. And so if you're the kind of person who likes to peruse YouTube or the internet in search of more information about everything that we learn, molecular orbital theory can get very complicated very quickly. All right, well, let's talk about molecular orbitals in the bonding of hydrogen, right? The simplest possible molecule that we can have. Everybody who's hearing the sound of my voice knows that hydrogen is made from two hydrogen atoms, right? They each have an unpaired electron, and they're going to approach each other, right? And they're going to get so close that they're going to share these electrons, and they're going to form a bond when the attractive forces between the nuclei and the electrons are maximized, and the repulsive forces between the electrons and the nuclei are reduced, or minimized, is what I should say. Well, if we think about molecular orbital, molecular orbital theory, rather, this is the way we're going to think about it. Here's one of those hydrogen atoms, 1s1. Here's the other hydrogen atom. It's 1s1 as well. Now, what's going to happen is when those orbitals come together, there's two possibilities, right? Remember that we said that an orbital it can behave like a wave, right? It has a wave function. Or an electron, it can behave as a wave function. Well, we can think about the waves overlapping constructively or destructively, right? We can have constructive and destructive interference. If the two orbitals overlap constructively, we form a bond, and we call that a sigma 1s molecular orbital when we're making them from two 1s orbitals. Okay, so we call that a bonding molecular orbital. And a bonding molecular orbital is going to be lower in energy and greater in stability than the atomic orbitals from which it was formed. So that explains why the two hydrogen atoms bond together, because they form something that's more stable when they get into that bonding molecular orbital. On the other hand, if the orbitals overlap with destructive interference, we actually get a node in between the two orbitals. That means there's no electron density between them at all. And we form what's called an antibonding molecular orbital. And an antibonding molecular orbital has higher energy and lower stability than the atomic orbitals from which it was formed. So again, we're forming a sigma bond, right? But when we overlap the two atomic orbitals, we can form a bonding molecular orbital. So this is a bonding MO, more stable than either of the 1s. And then this would be an antibonding MO. Notice that the number of MOs is equal to the number of atomic orbitals. This is an atomic orbital, and this is an atomic orbital, right? They're both 1s orbitals. I have two 1s orbitals, and I have two molecular orbitals. What if I have p orbitals? What are the possibilities then? Well, we know that p orbitals can overlap head-to-head to form a sigma bond. So the top part of this slide here deals with sigma bonds, okay? And I also told you that they can overlap side to side to form pi bonds. All right, I went over that with you in detail this morning. So if I take two p orbitals, okay, and I overlap them head-to-head, right? If the two orbitals overlap with constructive interference, I form a sigma bond, right? That would be the two p orbitals overlapping head-to-head, like this, right? And they share two electrons. That again results in a bonding molecular orbital, and we would call that a sigma 2p orbital, or a sigma p orbital. I mean, here they're just using 2p orbitals. It could be a 3p, it could be a 4p, whatever. Anyhow, that's a sigma bond, okay? If they overlap destructively, then I have a nodal plane in between them. That means there's no electron density there, okay? And that gives me an antibonding. Notice, I didn't point this out in the last slide, but notice that the antibonding orbitals are denoted by a star. This one here is called a sigma. It says sigma 2p. This one is sigma star. So the star refers to antibonding. Well, the same rationale sort of applies to pi bonds. If I have my two p orbitals overlapping side to side, like this, and this is my best, artist rendition. They're supposed to be overlapping, and they're supposed to be sharing, two electrons in here. Well, that would give me a pi 2p molecular orbital, a bonding molecular orbital. And if they overlap destructively, then I get a pi star 2p, so an antibonding. Again, the bonding molecular orbitals are more stable than the antibonding molecular orbitals. In a pi molecular orbital, the electron density is concentrated above and below a line joining the two nuclei of the bonding atom. Notice that this is, their representation of what I have drawn here. And you notice that there's actually no electron density down here, right? It's all either above or below this line. Here are some rules that we need to take into consideration when we're looking at molecular orbital configurations. The first one I already covered with you. The number of molecular orbitals is equal to the number of atomic orbitals that are combined to form those molecular orbitals. The next one, the more stable a bonding molecular orbital, the less stable the corresponding antibonding molecular orbital. The filling of molecular orbitals proceeds from low to high energies. This is just like we saw in electron configuration. We always started with the lowest energy orbitals, and we started filling them up according to the Aufbau principle. Each molecular orbital can accommodate up to 2 electrons. We use Hund's rule or the bus rule when we're filling up MOs of the same energy, or degenerate MOs. the number of electrons in the molecular orbitals is equal to the sum of all the electrons in the bonding atoms. With all that in mind, let's talk about something else, something called bond order. Bond order indicates the approximate strength of a bond. And bond order is calculated as such. 1/2 times the number of electrons in bonding molecular orbitals subtract the number of electrons in antibonding molecular orbitals. Let's look at some molecules here. Okay? Everybody here is familiar with this molecule, H2, right? You've seen this molecule many, many times in this class, right? H2 is just this. Okay? Well, if I had an H2 plus ion, could that exist? H2, we know that exists. What if I had helium? Right? Could I put two helium atoms together? Right? Helium is a noble gas. Doesn't sound like it's very reactive. What if I had He2? Is that possible? Or what if I had He2 dihelium cation? Would that exist? Okay. Now, before we move on, you might be saying, like, Mr. Dion, what the heck are these molecules? H2 plus, He2 plus, He2. Like, you never talked about those, and all of a sudden you're throwing these at me. Well, the reason why we look at these kind of wacky molecules that we don't even talk about, throughout the rest of the course, is because they have the simplest MO diagrams, and they're the easiest molecules that we can choose in order to kind of demonstrate how molecular orbital theory is powerful. Now, let me show you. So if you can bear with me, I can promise you that you'll get something very important out of this. So until tonight, you've never heard me talk about H2+, right? That never came up. But we know that hydrogen has an electron and another hydrogen has an electron. If I have H2+, well, we're going to lose an electron, right? Okay. And we know that both of those that electron comes from a 1s orbital. So we're going to get a sigma 1s bonding molecular orbital and a sigma star 1s. Right? The same thing applies to all four of these molecules on this page because they're all involving elements from the first period. Okay. So again, H2 has 2 electrons, right? Well, that means that H2 plus, we remove an electron. So we've only got 1 electron. And that electron, according to the rules that we looked at in the last slide, is going to go in the most stable molecular orbital, the bonding molecular orbital. How do I calculate bond order, which is an approximate strength of the bond? It's 1/2 times the number of electrons in bonding orbitals, 1. Subtract the number of electrons in antibonding orbitals, 0. 1 minus 0 is 1 times 1/2 is equal to 1/2. So the bond order of H2 plus is 1/2. What does that tell us? It's not a complete bond, right? It's not a whole sigma bond, but it can exist. Okay? The only time a molecule cannot exist is when it has a bond order of 0. And you're like, well, we're getting there, aren't we? Yeah. Let's look at the bond order of H2. And they're kind of offset here a little bit as they go. So H2 has 2 electrons in bonding molecular orbitals and 0 in antibonding. 2 minus 0 is 2 times 1/2 is 1. That accounts for the signal bond in H2. And we know that that's a totally legitimate molecule. What if I had dihelium and I had a cation? Well, helium has 2 electrons, right? Helium is 1s2. So if I have 2 heliums, that's a total of 4. Then if I have a cation, you subtract 1, so that's 3 electrons. I have 2 in the bonding, and I have 1 in the antibonding. 2 minus 1 gives me 1 times 1/2, gives me a bond order of 1/2. It's still not like it's like a whole bond, but it means that this is possible. And it has been observed. Not a lot of it, but it has been observed. Small amounts of the dihelium cation. Now let's get to the last one. Helium. You can already see that the bond order is 0. That means it can't form a bond. It doesn't exist. Okay, there's no such thing as He2. It doesn't exist. If you're like, well, why did you put it in here, Mr. Dion? Just to illustrate a point. It's got 2 electrons in bonding MOs, and it's got another 2 electrons in antibonding. 2 minus 2 is 0. 0 times 1/2 gives me 0. And therefore, so if you're like, well, what's your point? What's the whole point of this? The point is it explains these four molecules here. It explains why this molecule is stable, why these molecules can exist, but only to, they'd be very unstable because they have bond orders that aren't one. And it explains why dihelium doesn't exist at all. Okay, now these are things that we wouldn't be able to explain as easily with valence bond theory, right? These are all these different methods of explaining bonding were all created by man, right? Lewis structures, valence bond theory, molecular orbital theory. Okay, just ways that we have to explain bonding in molecules. We use the appropriate explanation at the appropriate time. Okay? All right. Well, that I'm pretty tired. Let's maybe take a break here. You're probably tired of hearing me talk. I just realized it's 6:15, so let's take a